All right, so we're in section 13.7. So it looks to me like with this one, my writing is even worse. Looks normal. I guess I see the more subtle nuances of my terrible handwriting. Normal. All right. So we talked the other day, and we said when we have some function z equals f of xy, and when that equals a constant, this is how we found our level curves. When our f of xy equals a constant, we're on level curves. And we found that our gradient was normal to level curves. Well, just like when we have z equals f of xy, when we have some function of x, y, and z, equals a constant, this gives us a level surface. And we're interested in what happens with the gradient when we're dealing with a function f of x, y, z equals a constant. What happens on level surfaces? So, so let's say we have some function x, y, and z, function of x, y, and z equals a constant. And we have a position vector. R of t is a position vector describing a curve on the surface. So we have some surface f of x, y, z is a constant that gives us some surface like the ones we talked about on the demonstration. We have some surface, and RT is a position vector of some curve on the surface. So we're traveling somehow on this surface. So we're going to say that R of t, we're going to write a vector valued function for R of t. So it's x of ti, just like we've done before, plus y of tj, plus z of t k. So this is our position vector for this curve on the surface. So on the surface, because we're on the surface, we can say that f of x of t, y of t, z of t equals a constant. This curve is on our surface, so x, y, and z are on our surface, so f of x of t, y of t, and z of t are going to be a constant. That's going to be a point, that's going to give us some point on our surface. So this would give us some value for f. And it would be, because we're saying we're on this level surface, f is going to be c. So we're going to use a chain rule. And we're going to find df dt. So df dt using the chain rule is going to be the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt plus the partial of f with respect to z times dz dt. And what is this going to equal? 0. Derivative of a constant is 0. What is this? What is this expression? What's another way I could write that expression? Partial of f with respect to x times dx dt plus the partial of f. What's the total differential? So it looks like the total differential. Okay. Let's think. So the total differential, that would work. Let's think a little more about what we've been talking about recently. So we have a partial of f with respect to x times a derivative of x plus this quantity of y, derivative of y, plus a partial z, derivative of z. So what other quantity, what vector quantity does this look like? Anyone see it? All right, let me erase this. What is dx dt I plus dy dt j plus dz dt? Okay. This is just dx dt, dy dt, dz dt. So that's going to be r prime. What is df dx I plus df dy j plus df dz k? What is that quantity? It has to do with f prime, but what is it, Molly? This is del f. So what is this quantity where we have the x components multiplied plus the y components multiplied plus the z components multiplied? That's a dot product. So df dt is del f dot r prime of t. And that equals 0. So what does that tell us about del f and r prime? So del f and r prime are orthogonal.
What is that finding?
What's that?
What is that finding?
So we have at a particular point, so r prime is a tangent vector to our surface, and del f is orthogonal to the tangent vector. Well, we picked an arbitrary curve on the surface. We didn't specify what it was. So del f, our gradient, is going to be orthogonal to any tangent vector on the surface. R was arbitrary, so del f is going to be orthogonal to any tangent vector. So we're going to say r of t is arbitrary. So So del f is orthogonal to any tangent vector. So if it's orthogonal to any tangent vector on our surface, what does that tell us about del f? If no matter where we pick our points, any curve, if it's orthogonal to the tangent vector. Question, Cole?
Yeah, how come r prime keeps laughing in the direction of motion?
No, we didn't say this was in the direction of motion. We just picked an r.
Or
But yes, r prime is in the direction of motion. So if we're talking about this curve on the surface, r prime is going to point in the direction of motion, but r prime is also tangent to r.
But doesn't del also point in the direction of motion?
No, del f points in the direction of the maximum rate of increase of f.
Then how come last in that if you put the problem, you say that it points in the direction of motion?
Because the direction of motion was in the direction of the maximum temperature increase.
Okay.
That's what we wanted to happen.
So would they not be orthogonal in that form?
In the heat-seeking particle problem, no. In that particular problem, one, we were in the plane, so del f and r prime were in the same direction. In this one, we picked an arbitrary curve on the surface, and we found that del f is orthogonal to the tangent vector to any arbitrary curve on the surface. So what does that tell us about del f? If it's orthogonal to any tangent vector on the surface, it has to be orthogonal to the surface. So del f is orthogonal because it's orthogonal to any tangent vector on the surface, no matter how we're moving. If we find the tangent vector of that curve, del f is going to be orthogonal to the tangent vector. So del f has to be orthogonal to the surface at a particular point.
Is there like many del f's depending on what point you're looking at? Or is there like one del
Well, there's a del f, so depending on our surface, del f is going to be, there will be one del f for that surface, one gradient. At a particular point, we would substitute in x, y, and z, and we would get one vector at that
Just
point.
the operated part.
Right. 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 So then in each point we would plug in an x, y, and z, and we'd get a specific gradient vector for that particular point. But we'd have one function that would describe the gradient on the surface. Okay. So what we've just figured out is that del f, del f is orthogonal to a surface f of x, y, z equals a constant. So at any point on the surface given by f of x, y, z equals a constant, our gradient vector is going to be orthogonal to that surface for any point on the surface. So del f for a surface given by f of x, y, z equals a constant, del f gives us a normal vector. If we have f of x, y is a constant, del f gives us the normal vector to the level curves. If we have a surface given by f of x, y, z equals a constant, del f gives us an orthogonal vector to the surface. So now we have this orthogonal vector. We can use it to find things. So let's talk about how we're going to use del f as a normal vector. This is one of the primary ways that we're going to use the gradient is as a normal vector. So what we just found out is that if for our conditions f of x, y, z is differentiable, at some point and our gradient is not 0, del f doesn't equal 0 at that point. Then we have several things that happen. One, del f at our point is a normal vector to our function, to f, to our surface at our particular point. And what this is, another thing that we can conclude here is that del f at our particular point, p0, is orthogonal to every tangent vector of f at p0. So the gradient is normal to our surface, and it's going to be orthogonal to every tangent vector. We call the plane that is normal to del f at our particular point the tangent plane to the surface. So we can use the gradient as a normal vector to our tangent plane. So we can find the equation of a tangent plane at a point. But just like in Calc 1, when we found the equation of the tangent line, when we're talking about surfaces, we're going to find the equation of the tangent plane. And the gradient at our particular point gives us our normal vector to our tangent plane. And we call the line through our point in the direction of the gradient at that particular point is the normal line. So when we talk about surfaces, we're going to be interested in tangent planes and normal lines. So the gradient gives us the vector that is normal to our plane. That gives us our direction numbers for our plane. And the gradient gives us a vector that is parallel to our normal line. So the gradient is going to give us our direction numbers for our normal line. So the gradient is going to give us lots of information about things that we're going to be interested in with surfaces. So questions about our conclusions here. So the important thing to remember is that our gradient is normal to surfaces. The gradient function is normal to surfaces at a particular point. If we have some function written as z equals f of xy, we know that this describes some kind of surface, but this isn't the type of surface that we just talked about, where f of xyz is some constant. We can rewrite this capital F of xyz is f of xy minus z, and our normal vector is going to be df dx df dy negative 1. So our normal vector is going to be given by this vector. And if we have our function f of xyz equals a constant, our normal vector at our particular point is just going to be given by our gradient. So these are going to be our normal vectors to a surface at any particular point. If we have our surface defined as z equals f of xy, we can just rewrite it f of xyz is f of xy minus z. We can find our normal vectors. And we can use these normal vectors to...
Sorry, Mr. Beaver. Can we get a minute? I need to talk to you before third period. Okay.
we can use these normal vectors to find our tangent planes and to find our normal lines. So, everybody clear on what we've done so far? Nothing really complicated, nothing really that different. Just we're using our gradient in a little bit different way. We know that n is normal to our tangent plane. So at some point P0, where we have x0, y0, z0, and you don't have to memorize this equation, but this is how it works. So the equation of our tangent plane is, I'm going to write it this way, f sub x, x minus x0, plus f sub y, y minus y0, plus f sub z, z minus z0, equals 0. So if we have a point, we can find our gradient, and we have the equation of our tangent plane. This is our standard equation of a plane. And if z equals f of xy, we're just going to use the other notation, the other representation for our normal vector. Our plane is, our equation is f sub x, x minus x0, plus f sub y, y minus y0, minus z minus z0 equals 0. So now we have an easy way to find the equation of a tangent plane.
The first one is if it is equal to.
This is f of x, y, z equals a constant. So with the gradients, we have a normal vector to our surface. We can use that normal vector to find the equation of a normal plane, the equation of a normal line, tangent plane, equation of the tangent plane. Use the gradient to find the equation of a normal line, and we'll use these quantities later when we kind of put all this stuff together. All right, let me pick out a few examples that we want to take a look at. Yes?
When you rewrite z equals f max y as max y minus z,
Mm-hmm.
why do you use z? Why don't you just use some constant that you subtract?
We want our equation. We want it to be we want it to represent a surface. So if we said f of x, y minus a constant, then we'd be taking that z portion out of it, and the z is what gives us our.
But like, why do you have to subtract?
Because in order for the gradient to be a normal vector, we have to have our function, our surface represented as f of x, y, z equals a constant. In order for that analysis to work, we have to have f of x, y, z equals a constant. Because that's when we did our chain rule, the one side turned out to be 0, and that's what gave us our normal vector. Okay, that makes sense? Okay. All right, so for these first three, we want to describe the level surface. So I'm going to give you a function, and we want to describe the level surface. So we have f of x, y, z equals 3x minus 5 y plus 3z minus 15. So what would this surface be? So a level surface, what do we do for a level surface? We set it equal to a constant. So we can just pick a constant. What would be an easy constant to set this equal to? 15? Okay. So we get 3x minus 5y plus 3z equals 0. If we set that equal to 15. We're going to set, so we're saying f of x, y, z equals 15. So we're setting this equal to, it would be, so let's say negative 15. There we go. Set it equal to negative 15. Then we get 0. Doesn't matter what constant we use. So what is this surface? Plane. This is a plane. So if we're talking about level surfaces here, this would be a plane. How about f of x, y, z equals x squared plus y squared plus z squared minus 25. This would be a sphere, right? We could set this. We could say find the level surface when f of x, y, z equals 0. So we get x squared plus y squared plus z squared equals 25. So this would be a sphere. So the level surfaces of this function would be spheres. We get a different sphere for every constant we picked, but for one particular level surface, we would have a sphere. How about f of x, y, z?
If you were drawing these, you would just have like one plane, one sphere.
Right, we would draw one level surface, because otherwise you'd be trying to draw multiple spheres kind of nested inside each other, or multiple planes layered. But for each constant, you would get a level sphere, a level or a plane or a sphere. Just like for z equals f of x, y, we get level curves that we draw kind of concentric circles or concentric ellipses, something like that. All right, so f of x, y, z equals 4x squared plus 9y squared minus 4z squared, and that's our function. So minus 4z squared. Cone. So what would be the easy constant to set this equal to? 0, set it equal to 0, so we get 4x squared plus 9y squared equals 4z squared. So we're setting this equal to 0, and then so this would be, so the sides would be what curve in the coordinate planes? Sides would be lines, right? If I looked at just 4y squared or 9y squared equals 4z squared, take the square root of both sides and I get lines. So the sides are going to be lines, and then parallel to the xy plane, when z is a constant, we get ellipses. So this would be an elliptical cone. So the sides would be lines, and parallel to the xy plane, we would get ellipses. So it would be kind of a squashed cone. There would be, yeah, so it would be, you'd have one going up and one going down. Because when you take the square root, you get a plus and a minus. Last one, f of x, y, z. And we'll keep doing these surfaces because it's going to be important to be able to look at a function and have an idea of what kind of surface that you're dealing with. Surfaces will hopefully be our friends by the end of the year. 16x squared minus 9y squared plus 144z. That's our f of x, y, z. Has to do, so there's going to be hyperbolas involved, and what else is going to be involved? Parabolas. So a hyperbolas and parabolas. Hyperbolic paraboloid, saddle shape. So this is a hyperbolic paraboloid. The level surfaces would be hyperbolic paraboloids. All right, so let me pick out we'll do one we'll do one example of finding a tangent plane and normal line, and then we'll be done. All right, so we want the tangent plane, and symmetric equations. For the normal line, 2x squared minus y squared plus z squared equals 0 at at the point 5, 13, negative 12. So we want the equation of the tangent plane, and we want the equation of the symmetric equations for the normal line. So what's going to be our first step here? We need to find the gradient. The gradient's going to give us the normal, not the line, but the vector, normal vector. So the gradient's going to give us our direction numbers for our line and for our plane. So del f, and I'm just going to write some steps here, gives a normal vector. So we have f of x, y, z here equals a constant. So del f is going to give us our normal vector. So del f, our gradient here is going to be, what's going to be our gradient vector? 2xi minus 2yj plus 2zk. Whoops. And at our point, so we're interested in this particular point. If we substitute our x, y, and z values, del f is going to be, what I came up with is 10i minus 26j minus 24k. What if we wanted a unit normal vector? What would we have to do? Divide by the magnitude. So some of your problems are going to ask you for a unit normal vector. You need to work with a unit vector. So if you need a unit vector, you divide by the magnitude. So our direction numbers. For a plane and for a line, you don't have to use a unit vector. Just the direction numbers, that's just going to make your vector shorter or longer, but it's still going to point to the
In the
same
last
direction.
section.
Because when you're finding the directional derivative, you need del f dot a normal vector, or not a normal vector, a unit vector. So because otherwise your directional derivative is going to be changed by the magnitude of that vector. All right, so our direction numbers. A equals 10, B equals negative 26, and C equals negative 24. And we're set to write our equation. So our equation for our tangent plane, what's our equation going to be? 10 times x minus 5 minus 26 times y minus 13 minus 24 times z plus 12 equals 0. So there's our tangent plane. And del f is parallel to our normal line, so del f also gives us our direction numbers for our normal line. So our symmetric equations, remember how to write symmetric equations for a line. X, right? So we get x minus 5 over 10. That equals negative y minus 13, I'm just going to write the negative sign there, over 26, and that equals negative z plus 12 over 24. Those are symmetric equations for a line. So that's going to be the symmetric equations for our normal line. Questions? All right, so what we've done in the last couple sections is we're kind of building up a toolbox of things that we can do with the gradient. You know that the gradient we use a gradient to find a directional derivative, the rate of change of our function in a particular direction. The gradient gives us a vector that is normal to level curves. if we have z equals f of xy, our gradient is normal to level curves. And we just found out that the gradient is normal to level surfaces as well. So gradient gives us a normal vector to level curves, normal vector to level surfaces. On a surface, the gradient is going to be tangent to any, normal to any tangent vector on the surface. So if we're talking about tangent vectors, our gradient is normal to a tangent vector. And what else did I want to, there was something else that I wanted to make sure you guys remembered. And we talked about a little bit on the demonstration. If we're on a level curve, so we have z equals f of xy, and we're on a level curve. You know the gradient points in the direction of the maximum, is normal to the level curves, and the gradient points in the direction of the maximum rate of change. What did we say is going to be the direction of no rate of change if we're on a level curve? Perpendicular to the gradient. If we're in the plane, and I mentioned this the other day also, if we're in the plane and we have a vector, how do we find a vector that is perpendicular to that vector in the plane? What's the easy way to do that? Easier. Easier. Switch x and y, change the sign on 1. And that's, no, we're on a level curve. We're on a level curve. So we have some vector that's just an I and a j vector. To find a vector that's perpendicular to that vector, switch the x component and y component, change the sign on 1. So if you're on a level curve, you know the gradient. That's normal to the level curve. If you want the direction of no increase, switch the x's and y's of the gradient, change the sign on 1, and that's going to give you a vector that's normal to the gradient. And that would point in the direction of no change. All right, homework. There you go.